So let's recap the stuff. So now we are in this measure space. So usually the notation is well, space, then you have the sigma algebra, so you call it a measurable space, you can put a measure on it. And finally, if you add the measure, it's a measure space. And this guy is level. Okay, and then, okay, the observation is essentially that, okay, the most important part is the regularity, so the V is contained in L, and these are the Borel. And, well, if, well, and for any E there exists G delta set, such that the measure of E minus G is equal to 0, and E is contained in E. So this is the outer, and then you can get the inner regularity by taking the components.
I think G should be substitute E.
Yeah, you're right. Yes. Well, it's fine. Okay. So after that, well, now we have what is a measurable function. So it's f to the minus 1 of any open set, and actually in R it's just intervals belong to the sigma algebra. So it's open. And the subcase was, so for example, if f to the minus 1 of O is in Borel, then f is really measurable, and let's call the measurable like L0. So this is L0. And then the regularity here, so essentially I want to restate what is the regularity there. The regularity is a particular continuous function. So the reason for the regularity is that, well, first of all, what is the important stuff is that the most important, so here the most important is that the measure is sigma additive, no? Remember, the measure of the union of this joint is equal to the sum of the measure of the disjoint of the sets if disjoint. So these are disjoint. Well, you don't need to write it. This was what we wrote last time. So now for this guy, and the most important thing is that Fn converges to F pointwise. And then I can also cancel a set of measure 0. So let's say M almost everywhere. So it converges pointwise up to a set of measure 0. Sets of measure 0 are eaten here. Because from this guy, essentially every set is a Borel set with a set of measure 0. So pointwise then F is in L0, if they belong to L0. So actually it is a very strong stability condition. And then, so now I want to use the same, well, the same, let's say, translation table here. Here, E is essentially open. So here it means that if F, now we have the two properties. Say this is Egorov. So if Fn converges to Fn, well, we just need pointwise, doesn't matter. On E, and the measure of E is less than plus infinity. Then for all epsilon, there exists k epsilon compact containing E. Now we have the measure of E minus k epsilon is less than epsilon, which is the choice. And Fn converges to F uniformly on the compact set K epsilon. So essentially, like here, we are not moving very far away from open sets. Here, we are not moving very far away from uniform convergence sequence. And the next one is essentially, really, we are not moving very far away from continuous functions. So if f is in L0, so everything here is in L0. Then for all epsilon, there exists psi, which is continuous in R. And the compact, and well, such that the measure of the set where f is different than psi is less than psi. So we were going to work about this losing part. So philosophically, well, or in a mental language, not in a mathematical language, what I'm saying is that I'm always adding set of measure 0 to the standard continuous function on a compact set. But clearly, then there is the technique to make it formally correct. So this is just how the way of thinking. Well, it's not, if I can assume that the function is continuous and it converges, then and the result seems correct there. But now the technique is to make it work into the general case, so into the real case. And that is not easy, like for the losing theory. The losing theory needs some, let's see the proof. Losing. Okay, so the ingredients were clearly, well, you suggested already the ingredients, no? Well, essentially, I have that, so from this guy, another basic property is that if f is, for any f, I have a, sorry, if f is measurable, I can approximate by simple functions up to a small set, and these simple functions, well, okay, in every set of finite measure, be careful. So let's put the ingredient here. So the first ingredient, well, the basic ingredient is this guy. So if I can construct a sequence of continuous functions converging, then the limit is clearly continuous on the compact set because it's uniform convergence. So this is the basic ingredient. So let's say the key is ego plus Fn continuous. So now I have to construct the Fn continuous. And then I recall some property here that, well, if F, so another property, if F is in L0, and let me say, well, actually, let's say if F is bounded, then, okay, there exists a simple function which approximates uniformly. Phi less than equal than F, psi, let's say an epsilon, for all epsilon. There exists this guy, and phi epsilon, psi epsilon are simple. And I have that psi epsilon minus phi epsilon is less than epsilon. Okay. So the idea is always to say, well, we construct it explicitly. Now you take the level set, and in one sense you give, for psi you give the lower value, for phi you give the lower value, for psi you give the upper value. And then you are sure that it stays in between. So you add the one epsilon. Okay, let's say this. So the only thing is that there are two problems here. So the F is bounded, and well, this holds also if it is not measurable. So let's say if F is measurable, I have that phi. If F is in L0, then also phi epsilon, psi epsilon are in L0. So at this point, the last part is that essentially I want to touch or smooth out essentially these two functions, or one of the two, doesn't matter, in order to have something continuous. So last step is that psi or phi, let's say phi epsilon.
Excuse me, but why is this true that if f is measurable, then both of the simple functions are measurable? Isn't all simple functions?
No, you can take. I mean, it's not true that you can take any approximation is measurable, but you have approximations which are measurable.
I mean, why does this depend on f being measurable?
Because otherwise, if they are measurable, they converge, then the limit is measurable. If it is measurable, you can construct them to be measurable.
So here we say there exist.
There exist, yes. You can take, this means you can take them.
Okay.
You can take, because you can approximate zero uniform with something non-measurable. So the last step is phi epsilon is simple, then, and I have to be careful, then exist, let's say. We have to make it a little bit formal, and indeed let's put this guy exists, let's say psi epsilon continuous. Let's say psi epsilon different than psi epsilon. The measure is arbitrarily small. Well, and now one can imagine something that, okay, I can make this arbitrarily small, so essentially I throw out a small set because I do the family. Here I move something whose sum is arbitrarily small, and then I get something continuous which converges to f, and then by Egorov, if this converges pointwise by Egorov, I make it uniformly, and then I'm fine. So, but we have just to, so there is something here that I have to remove, no? Okay, the line is correct. So, but clearly I'm doing for something on the bottom, no? Because I know which theorem I have to use, and I want to see which steps I have to perform before. So I have to start from here, no? So here the two problems are that the measure of the set E is less than plus infinity. And here I have the boundedness, no? And then let's see about this guy. So let's remove immediately the measure of E less than plus infinity, because it's the easiest to be thrown out. So, well, let's say step 0. Okay. If, let's say, the theorem can be done as I want. Let's say in, okay, let's do like this. Is for every interval AB the statement of losing holds in AB, then it holds in R. Okay, so what is, now I have to choose the AB. Last time I said minus n, but I think it's even easier to think something like, so let's say proof of this point.
You can decompose the epsilon to sum of epsilons and apply it for every
interval. Is the standard stuff. Yeah, this is, so I want to ask if you see the line of the proof now for this step. Who sees the line? You and the others? You see? Others? Okay, this is a good exercise. So I want you to, I do some pieces and then I ask again. Okay, so let's do R. I write R as the union of, let's say, n in Z, n plus 1. Do you agree? Okay. Does anybody of the rest of the class see how to do, what to do next? Okay, this is an interval, no? So, well, I say an open interval doesn't matter because n is measure 0. So let's put something like that and it is even better. So I'm not because otherwise, okay, I have to think the point is measure 0. I can always try to add, but so now it's clean.
We can multiply epsilon by 2 to the power minus.
You know. I know that you know. So for the other, what do I do next? And suggest we can also say, well, I just leave for half an hour and then I hope that the idea comes. Okay, I now apply losing. Is that okay? I apply losing that. So let's repeat what losing says. So I'm saying that for f in L0 now only of this set there exists, so for all, so the epsilon now depends on n a priori, no? So I choose an epsilon which depends on n. There exists a psi which depends on n, which is continuous, but I can say continuous in n plus 1. And the measure of psi of f different than psi n only in the set n plus 1. So this is the statement for losing is less than epsilon n. Okay. So I just copy the statement of losing theorem in the set ma n plus 1. So I'm saying that this holds in this set, it means exactly this fact. And then I'm free to choose this value arbitrary. So you choose a value arbitrary and I give you a function. This is not arbitrary. Okay, next step. Yes, next step, choose epsilon equal to epsilon n to the, well, yeah, to the minus n is okay, doesn't matter. You get 3, but it's fine for you, no? Or get 4. Minus modulus, no? Okay, so now what I can say from this choice. So I say, so this set, so the set where f, so I define a new function, I need to define a function. Define, yeah. Let psi be the function.
When x is just sigma n of x, so when x belongs to the interval n to n.
Then the measure where f is different than psi, now in all R is the less or equal than the sum of this epsilon, but the actually is equal. Well, is equal because this guy has measure 0 and they intersect.
Okay, but is it well defined in the series?
Yes, we have to see, indeed. That's the point.
To what?
If it's well defined.
Yeah, in n, in the values in Z, it is well defined. Because you see, they superimposed, no? I'm cheating. Because I knew that I said the open, but. Okay, let's go. Well, the measure of this is less than 4 epsilon, let's say. Actually, it should be 3 epsilon, probably. Okay, is this well defined? And it is continuous. So well defined.
Clearly, this one is continuous. The problem is at n. If it is well defined at n, it is continuous.
Okay. Yes. It is well defined. Okay, let me do something. So let's call this set the set where f, let's call the good set, is the set where f is equal to psi n intersection n plus 1. Let's say like this. And now I say that the function which I just want this function in the union of the good set. Is this well defined? Why?
But see a problem.
Because we just by definition we restrict
maybe
to
not good
this thing, and
always.
this thing is by definition is where it is they agree. So.
They agree with f.
Yeah, they agree with f.
So it's okay. And then it holds, then f equal to psi n complement as less than epsilon. Is psi continuous on this set? But is this set closed? Well, I can take this set to be closed, no? Because of the regularity. Actually, it could be compact here, compact. Inside each interval is compact, because, okay, you give me a set that just restricted, you need to make it closed, and since it is bounded, it's compact. Okay, so this set is closed. So it is psi continuous on this set here, the good set. It's in G.
Yes.
Why?
Because at any point it agrees with this. I don't know how to pronounce this symbol. N, and it is continuous by definition. Xi n, and xi n is continuous at this point.
In n, if we take a point n, maybe you have some suspicion, but on the left is continuous and on the right is continuous by construction. So it is continuous. So psi is continuous on the set of definition, which is G. So so essentially you have everything for losing, but that psi is just continuous on a closed subset. And now I need to use the property of the topology in R. So you have a function which is continuous on a closure, on a closed subset. You can make it, but actually you can make it continuous.
So we have a function
which is continuous on a closed subset of R. So for any point of that subset, you have the properties of R. Then the function is continuous. There exists an extension. So from now, the last step is I erase. I think this guy is not in there. So psi is continuous on a set n, and f is closed in R. Then there exists, let's say, psi tilde, which is continuous in R, and psi is equal to psi tilde on f. So the question is, how many of you know of this property? Otherwise, we can prove in R is very easy. Usually, it's an assumption of the topology. I think T4. I'm almost thinking that it's T4. One of the separation properties. Okay, so let's do that. Here is very easy. So do we agree that if I can prove this property, is done? This psi I extend and it's done. I see that it's not Friday only for me. Unfortunately, next week we have 4 lectures. This is a problem with the schedule that cannot be solved. Clearly, now that the course becomes a little bit more requiring, intensive, clearly I know this can be hard. So let's prove this property. So let's take the complement. So this is open, no? And so it's the union of some intervals disjoint. Okay, so can we make an extension now?
The problem, we know that if we have the topological spaces, for example, T4, normal, we have closed 2 disjoint closed sets, we can make a continuous function such that it gives, but here
1 to 0.
Yes, but here, how do we give the other clauses?
Yeah, here, okay. The closure is that you take any subinterval here, any compact subset of this guy, the union is a closure.
Could you read again?
Take a compact, well, in that case, well, you take say something?
Yes, you were saying that if you take the interval.
Yeah,
inside,
indeed, okay, indeed, here is a special one. I think, yeah, indeed, let's do that. I think you can use T4, but let's do it in special case. So here, the thing is that if I have AI and BI, so these are the limit values. They the values on the boundary, they exist because psi is as one value, no? So just connect arbitrarily, for example, like this one. So, for example, define psi tilde on, let's say, any point in between is 1 minus t a plus t bi. This is a point in between, is equal to 1 minus t psi of a, which is defined, plus t psi of b, which is defined. So now psi tilde is defined. Is this continuous? Yes.
Yes.
So in G is already continuous. Take a point inside, clearly there is an idle where is in between, so it is continuous. So any continuous extension here works.
These intervals are
Disjoint.
disjoint.
Disjoint, yeah. Is the connected component of the O, so the largest. Given a point in O, you take the largest interval containing in O and containing that point. And this is well defined, and that's the okay. So in this setting, what we did, well, actually, I'm removing this thing, so I'm fine now, no? I can just prove the statement into a bounded interval. Do you agree? So it's just this. It's very important this line of code because it shows all the steps. You know what you have to use, and then you have just to adapt. So now the next problem is bounded. So let's go to F bounded. So the idea is that, well, if F has real values, at some point, and the level set where modulus of F is larger than M, well, should go to 0, should disappear. The intersection of them is the empty set. I don't have any point whose value is plus infinity. And indeed, if you try first to give the bounded, now we will see that you have still to restart with the finite measure. Okay, so now step. I said 0 earlier, so let's say step 1. It should be 0 because I'm not doing really the proof. I'm just saying this is some observation which works no matter what. Or 0, 0. Okay. So I want to say something like this. If f for all epsilon, there exists m such that m, the measure of the set where the modulus of f is larger than m is less than epsilon. Okay, you see, I'm not writing that I'm doing in a subset of finite measure, but okay, proof.
Assuming that f is bounded?
F, no.
In general?
No. Yeah.
For any measurable function f?
Yeah. But there is a glitch here, so, okay. Does anybody see how to do the proof? At least the basic, the fundamental property I want to use. I want to use something, and then I have to adapt that in order to get the proof. Any idea?
Let's assume it is not true and derive a contradiction. That it is
Right. Yes.
because if this is not true, then there exists some epsilon such that no matter which set I take, the measure no matter how big m becomes, the measure of the set where f is greater than m is greater than epsilon.
Mm-hmm. So if not,
Yes.
There are
So I can take the intersection of if this set is for every m I get this set.
there is a problem. For example, you can take an interval example.
then take the intersection.
Yeah.
F is plus infinity, unbounded exactly where it is inside on the intersection of all these sets.
It is empty.
This set.
Yes.
Why?
Because if can't
Yes.
yeah, because if can't take the
Only
value
are
of
values. Yes. Now.
Therefore, because then the measure of this intersection is 0, a measure of phi is 0, right?
Yes.
So for every epsilon,
So you want to use the following property. So the limit is what we want to do.
yeah. Now because we meet this
So
epsilon,
this is 0, and
Yeah.
then you say the limit is 0.
but now we fixed an epsilon. If I take delta
Yeah.
smaller than epsilon, I get the
But
contradiction with
when
this.
this hold? When does this hold?
Because the intersection is empty.
Yeah, but there is an assumption here.
They are monotonic.
No. Because I can take the intersection over I less than j and the limit over I less than, for I less than j and limit over j. That's not a problem. In any case, they are monotone. Who said that? You said that?
Finite
finite measure. Finite measure, because otherwise the intersection, remember the intersection of n plus infinity is equal to empty set, but the measure of n plus infinity is plus infinity, and the measure of the limit is 0. Never works for plus infinity. Yeah. So it's okay. Yeah, indeed the proof is correct, but then you observe that the measure of f greater than mi is less than plus infinity for some I. And so,
if we take delta smaller than epsilon, we have fixed epsilon now by assumption.
No, but then if this holds, it's fine, because then you see that the intersection of this set goes to 0, so it cannot be epsilon. So now it's a contradiction.
Yeah.
So if you assume this, from this observation, you have that the limit of the measure of the, let's say, the intersection, which is essentially mf greater than mi, is equal to 0,
yeah.
contradicting the yes, under this guy. So, and now what I can just say, this guy, I mean, this assumption has already been accepted by step 0, because we know that I need just to prove losing in a bounded set. So certainly it is less than the measure of the interval. Okay. By step. If you try to start with this step, well, you discover that you need to prove this guy, and then you have to get back. Okay, so now we are fine, bound. So we have now the phi epsilon and psi epsilon, or E one of the two, let's say phi epsilon. Last step, well, last preparation step. So you see, this holds independently of the proof. These are properties that are just like exercises. So show that if it holds losing in a compact set, then it holds forever. Okay. Show that if f is bounded, then it is essentially bounded, is essentially uniformly bounded. Well, sorry, if f has value in R, it is essentially bounded up to, sorry, which means it is bounded up to an arbitrary small set. Second law. Third property, show that if f is simple, there exists an xi continuous. 0. Because this is something that is independent. It's a good exercise, actually. Okay, let's do this. So phi simple in, let's say, a bounded set. Okay, let's say it takes an interval, doesn't matter. In A, B, or closed, it's not matter. Then there exists xi continuous. Then for all epsilon there exists xi continuous, such that the measure where phi is different than xi is less than epsilon. Any idea here? So it's nice to decompose the problem. And actually I can require even more, so I can require phi, psi, well physically you can require less or equal to normal phi. But this is, you just cut the any idea?
If we have something like this, we can just eliminate a small bit of the edges and connect it by a line. But it depends on the difference in heat. We choose how small we eliminate the point, such that when we make the sum, it becomes smaller than the edge.
Yeah, the idea is good. The idea is correct. But you now have to work with one of the principles down there. It's already written.
This is already what?
It's already written. So Well, let's do a simplification. Because a simple function can be complicated, but let's do a simplification. So, suggest me a simple simplification instead of a simple function, something even more fundamental sense. So if I can prove for that case, I can prove for any simple function. So what is a simple function?
Sum of indicators.
Now I are measurable. I need that is done. Otherwise it's false. Okay. You see any simplification here?
We only take two elements. The sum is only two.
Just one. If you do one. So if, let me say, if 3i and for all epsilon there exists, let's say, a function, continuous function psi, which depends on I and epsilon, such that then the step okay, how many of you agree with this statement? The statement is that assume I can prove this statement only for as the simplest simple function can make, which is the indicator function of a given measurable set.
Yeah, that can be AI disjoint.
We can also use the same trick of decomposing the epsilon.
Yeah, you can take this joint, but you don't need, no?
We can also make the same trick of decomposing the epsilon and using
Yes.
it for every one.
Here is even easier, it's a finite sum. And so you are fine, because if you sum countably many continuous functions, you may be in trouble. But finite sum of continuous function is a linear space, so it's fine. Yeah, how to prove it? Well, just say that define the psi there is the sum of psi of each element ai and the epsilon divided by, okay, this is a sum up to n.
Epsilon over n.
N. So in the, I remove how much, at most I remove epsilon over n times n. So I remove epsilon, in the rest, clearly they coincide. Sorry, ci, otherwise they don't get correct. This works. And so we are happy. So at this point we have only to prove the statement for a characteristic function, an indicator function. And now how to do that? This will be losing for indicator function. So you see, I decompose the problem, and in the end I arrived that essentially the last step is losing for indicator function. The previous step, okay, everything works now, because I already reduced these two. I can put them into the statement, into the assumption of the statement, and I'm fine, because I know that if I can prove the statement with these two, I can prove the statement for the general case. And finally, once I prove that, from here to here is what is the construction of a approximately simple function. And here just observe that essentially the losing theorem reduces to the proof of the losing theorem for indicator functions. Yeah. And it's always like this. You decompose, at the end you arrive to something which is almost trivial. And here I'm saying it is trivial. So I want you now to give me how to do that. And here you use really T4 actually. Yeah. Here is definitely T4. Okay. I need to use some property of measurable sets, no?
We use the
so let's see. So regularity. And then I use the separation property. Okay, regularity and separation property. So regularity is that I'm given E is contained into an open set O and a closed set, say F, and the measure of O minus F is less than epsilon. And now what would be my function? So I need xi such that xi on on F is equal to 1 and xi on R minus O is equal to 0.
Yes.
And then this works. So these are two closed sets.
This is a theorem we covered in topology. It is very well known.
Yeah.
I don't remember, but we proved it. It is called.
Horizon.
Yeah, horizon.
Okay. So now extend. So uso them or whatever. So extend. Between 0 and 1 in between. You don't need this step, but actually if you want to preserve that something like psi is less than the sup, less than the inf, so you can preserve the bounds. But you don't need really that. So let's recount.
Is there a similar way to prove this in the special case of R?
Yeah, the one that we did before.
The one
that we did before, because you have two closed sets and then you fill the open when you as you want. Okay, so let's recap. So first, I know that I want to use a growth because I want to build a family of continuous functions. The conclusion is that clearly once I know from this step, I know to approximate the indicator, I know to approximate the simple, and then I'm removing arbitrarily small step, a small function, so I know how to build a family of continuous function which approximate like here. If f is bounded and the measure is finite. Then I observe that if f is bounded, if f is not bounded, I remove a little bit more and it's still bound and it remains bounded. And if this is not finite, I can do in pieces and then I just join, extended, excited, I construct. So let's now finish by put in some arrows in the proof. And so now it should be clear. So I start with the following. So let's say if I want to convex, so if f is the indicator function of E, then using is okay. So there exists this psi which depends on E and epsilon and the measure of E minus psi. Sorry, different is less than epsilon. Okay. Now from this I move certainly to simple functions. So if phi is simple, there exists for all epsilon, there exists psi, epsilon, and now it depends on phi, such that the measure of phi different than psi epsilon phi is less than epsilon. From this one, I know that they approximate. Okay, so here the trick is that epsilon is equal to epsilon over n if phi is equal to sum over n of ci. Okay, I should be put epsilon I should be epsilon over n ci because it's multiplied, but doesn't matter. I just put a little bit, I just remove a small piece at any level. Okay, now I can do that thing because this converges uniformly, so it means that now what I use? From this theorem, so from this approximation, phi epsilon converges to f pointwise. From this guy, I can take epsilon at, so let's say epsilon I is equal to epsilon 2 to the minus I. Then I get that psi epsilon I phi I, my approximation, converges to f pointwise up to a set of measure epsilon, because I remove every time I remove this piece. If I remove all pieces, phi is equal to this guy, and this converge point is converge pointwise. So here I get the next step, which means that there exists psi continuous, so I and psi converges to f bounded up to a set of measure epsilon. Okay? So now I want to remove the boundedness. So if the support of f is bounded, then f is bounded up to a small set. Because essentially it's the observation that when n grows, the set converges to the empty set, so its measure is arbitrarily small. And so this implies that so by Egorov, now I can apply Egorov because it means that this converges to f. Okay, sorry, let's add the step. So there exists psi I, which is continuous now in bounded intervals, and psi I converges to f in A, B, up to a small set. So I prove the losing theorem in any bounded interval, any bounded set. Finally, so now I apply Egorov. I deduce that f is equal to psi continuous in every bounded interval. Because up to a small set. Okay, if you want to keep track of all the epsilon, well, they become larger and larger, but that's not the important thing is that I do finitely many. And now the last step is that if it holds in any bounded interval by standard covering, by say, R is the union of n plus 1, then losing holds in R. This was the line of the proof. Questions here? There are something are good exercises actually. They don't ask you to prove losing theorem, but maybe they ask you prove that if f is so the set f is essentially bounded. Or prove that so simple function can be approximated like this guy. Because this is independent of the proof. It's something that always works. But clearly, once you have these two theorems, you can apply these theorems to prove the statement, no? Because the fact that you can apply simple function is simply the losing theorem applied to simple function. Okay, so I think okay, let's do some exercise. Let's construct a simple function which cannot be approximated by step functions. Well, simple functions are more general, clearly. So let's say the exercise has several variables. So for example, construct simple function which can be discontinuous at any point but is measurable, but we require measurability. Really, this is exactly. Okay, so if it is discontinuous, so at any point it cannot be approximated by step functions. But okay, we'll see later.
0, 1. The rationals.
It's not important. We choose which one.
Take the function that is 1 in rational and 0 in irrational.
Let's put it this. So what is the statement of losing here for this function?
That there is a continuous function that approximates
Which
this,
one? Which one?
The constant function 1.
1.
Sorry, the constant function 0.
0.
0. So on a set on of full measure here. So let's compute the Riemann integral here. What is the Riemann? Well, the Riemann integral. We can compute the Riemann integral. We can compute the sums and take in the limits.
It's not integrable.
Y is 0.
It's not
One is
integrable.
0, the other one. Okay, and now what is now, okay, this is just a jump, but what would be the measure, the integral of phi for the back? If
Zero.
the theorem is 0.
0.
Should be the measure of Q 0, 1. If you think it's 1, so this I cannot renounce to that property. No? The measure, the integral, the indicator function of a set should be the measure of a set. This cannot be avoided. I mean. Okay, so this is 0. And now let's, because this is the next step. So let's imagine I want to do the same trick as the Riemann integral. So I'm saying I'm approximating by above, by below, by simple function here. So what is the basic property that let me compute this to be 0? So I approximated below by simple function and above by simple functions instead of step function. I know it's almost tautological here. It's that phi itself, it's already in the class of my test functions. No? It's not a step function, but it's a simple function. And Lebesgue computes integral for simple functions. And then you pass to the limit. So that's the basic property. You see, we already used this equivalence. And another one is, we did last time. Now, if m is plus infinity, then it's false. We did this exercise last time. So now we start with integral. Are there questions up to now? I mean, this fourth of the board is the fundamental part. It's really fundamental. If you understand the various steps, so that it's the pointwise conversion makes measurable, you have this approximation here. So there is one piece more in this part, and then you have the three regularities. You know how to compute the value m of any set. You know that this is additive, and this property, if you digest that part, basically you have the fundamentals of the theory. Now, so we keep this fourth. Okay. So let's have some fun about the Lebesgue integral. So we start with what is the definition of Lebesgue integral for simple function. If phi is the sum up to n of ci some set pi, then the integral of phi with respect to the measure is equal to. Sometimes they don't put the measure here.
Summation of CI, measure ER.
Some CI.
Yeah. What exactly? There is only one choice if I want to be coherent.
Otherwise, no one would be interested in this.
Yeah, there is only one problem here. If one is minus 1 and this is plus infinity, and the other is 1 is plus infinity, okay, so let's
That
say...
is 0. Right?
Yeah, is undefined. So we need to assume that or equivalently, is contained into a bounded interval. Because otherwise this form is not determined. And indeed, for example, the integral from 0 to plus infinity of sine of x cannot be determined. So now it's fine, because the sum over here is meaningful. They are just in R. I'm not using any extent.
Excuse me, but here you say that the measure of EI is less than infinity for every I, or what?
Yeah, for all I there should be one. Well, maybe just one can be plus infinity, and then the integral is plus or minus infinity. But we will see later how to compute this case. These are always extreme.
Just writing all one.
Or if every I is contained in an interval. So it's finite dimension. Okay, so let's see some. So what is now the integral?
And do we here in the notation integral phi m or phi, what is the notation?
Okay, there are several notations. Here is a little bit a mess. Because it depends on the branch of analysis in which you work on. So sometimes you use the notation integral phi of x dx, which is like the Riemann notation. Sometimes you use just phi dx, phi, whenever the measure is clear. Here we have only one measure. And finally, you have also phi m dx, which is the one that, so phi m, phi x m dx, or phi dm x, phi dm. So 7.
So sometimes they put the measure.
Hmm?
In probability, usually they put the measure first.
The measure first, also the engineering do like that, because otherwise they forget. But I'm an engineer, so yeah, okay. Then you can put the dm. I don't know if they put dm phi or whatever. In my opinion, the most correct one is this guy. This one and this one. These are the most correct one, because the idea is always that so m is something which gives a value to something, and in this case, is a reminder of the Riemann integral being related to dx. But actually, I'm not saying that is the most common use is this guy and this guy. But okay, we decide. I will stick with my notation simply because. But here it's easy. It's always it's a Riemann integral. Sorry, it's just the Lebesgue measure. Okay. And now let me. What is? Fine. What should be the integral over a set?
Put the indicator inside.
So it's always equal to 5 times the integral times the indicator function of t integrated. Okay, so these are the definitions. This is what you cannot require anything less. Okay, so now let's start with some proof. So let's say EI disjoint. So this is L. Then the integral over the union is the sum of the integral over AI. They are counter-repeating, no? So this is I equal to 1 to plus infinity. Proof. There is nothing difficult here.
We just take the thing on the left minus partial sum, and we complete the difference.
Yeah, you can do that, or you just apply the definition. The sum is absolutely converging because of these assumptions. You cannot have something worse. And so you can just decide rearrange the indexes. So, okay. I leave you by exercise. This is just a rearrangement of the indexes. Okay, just a remark. If E as a finite measure, you don't need clearly to require this assumption here, simply because this sum is finite measure. So just every time you do something, be careful not to have plus infinity. Plus B should be a study on its own. Okay, so well, this is something that
we just in this formula substitute E. We substitute E for the union, and because EI and EJ are disjoint, then EI intersection the union becomes EI EI itself. But we have also a sum over I, and we use the measure distributes over disjoint set.
Yeah. Yes, it's here. Yes, exactly. It's just that the proof. You write the two definitions, and you see it's just a rearrangement of the indexes. Yeah. So here the sum over. Now let's call it J. You have sum over J, and then sum over I. And here you have sum over I, sum over J. But since it is absolutely convergence, because of convergent, you can switch. Yeah, that's the only. So let's go on now. After this guy, what you expect is, so let's do the easy part. So if phi as before, so let's say the integral of a phi over, we can forget the here, is equal to a, the integral of phi. For any constant a.
We are working with simple.
Simple, because I just defined how to compute for simple.
Because that's true for finite sums. We can just take a
finite sum is simple. Finite sum. Simple is just finite sum. There was that he called semi-simple when the sum I never saw this.
Yeah, because if we write phi as the sum, a phi just I multiply.
This is straightforward. Just the definition. The a exits from the sum. Phi less or equal than psi, then integral of phi less or equal than integral of psi. Well, you see, yeah, should be like that. But actually, you need to use just the definition.
Yes. The value is less than equals to, so the summation is less than equal.
The sums, yes.
Yes.
This, well, which sum, by the way?
Ci. Yeah.
So you have, let's do that. I mean, it's nothing difficult, but. So I need just to use this, no? So I have that phi, which is the sum psi, which is the sum to m, let's say dj indicator function of fj. Just not to be confused. Okay, I have this relation. Okay.
Are the EIs disjoint or?
No, but we can go to define.
Because if they were disjoint, then the
In
CI
intersection
must
of
be.
AI and FG, in
AIJ
intersection,
as
in intersection, AI and FG.
Okay, so I want to replace phi and psi when these are disjoint.
Yeah.
Yeah, okay, so phi is equal to the sum over, and then let's put some constant alpha I of x, where alpha I of x is equal to 1 whenever x is in E1. This is, okay? And then it means that phi in, let's say, in the intersection over some, let's say, some EI, and then, okay, let's say, so this gives me the function, so let's say, so phi is equal to the, to the sum over Ci whenever x is in the intersection over alpha I of x is equal to 1 over the EI. So let's call now any, so the intersection of any subfamily. So if I say alpha 0, alpha n is in 0, 1 to the n, then I say E, let's call this beta. This beta is the intersection over the alpha I different than 0 than EI. Okay? Now E beta are disjoint. Well, I should make them disjoint, no? No. Yes, okay. Intersection, and then the intersection, they should not be, when it is 0, should be in the complement. Should be minus the union over alpha I equal to 0 of alpha j equal to 0 of EJ. So if I give a multi-index here, I define the set where it just chooses the point where it is exactly 1 and they are not in the when it is 0. Now, E beta are disjoint, simply because if you switch one of the two, one alpha from 1 to 1, it is removed from, or it is added. And phi on E beta is equal to the sum over, well, this index Ci alpha I, where alpha 0, alpha n is equal to beta. So that's the definition. Yes, so you can make them disjoint and the value is computed. So for any point, essentially, first you take any finite subfamily of your set, take the intersection and remove the set where it is 0, and the value is there is exactly this value. So you can say that phi is equal to the sum, this value here, so now the sum for any beta, the sum for alpha 0, alpha n equal to beta C alpha phi, and the indicator function of E. Yeah, fine.
I think it also we can proceed as follows.
Take the 0, remove all the rest, and give the value. Then you take 1, remove
But
all the rest.
in this, we will need to change the coefficients.
Yeah, the coefficient, yes. Here.
Yes.
Yeah, the coefficient should be computed,
Yeah.
because when it is common to two sets, you have to add. Indeed, this is the value. So you give any subfamily are the points which lives only in the set where it is 1 or 1, and not when they are 0. And the value is the sum only on the value when they are 1. So it's written. Okay, so it is a little bit a long proof. I cancel. You don't need to, well, if you want to reproduce, it's a good exercise, but then I assume Ti and Fj disjoint. And this is a good exercise, no? I give you a simple function, prove that I can make it, and that I can represent as the sum of disjoint sets. In this case, the representation is unique.
Yeah, and Ci is less than Di.
Why?
Because if I take x in xi, in ei, sorry, then phi of x is Ci, and psi of x is Di.
Ci is less than Di only in the intersection.
Yes, and
Yes.
after.
On what intersection?
Of Ai and Fj in the common points.
Yeah. Sorry, yes.
After making this joint, we can say that.
Yes, we can take the intersection of ei. So I define aij equals ei intersection fj. Yeah, and since the sum is now double sum over i and j.
And then let me put here, now this is Ci, and here I put J, so the sum over J, and then I have less represent the sum over J, sum over I, okay. Now, these are disjoint. Now is the trick. These are disjoint, and so it holds pointwise. Okay, and then the definition works. Because integral phi what you expect. The only trick is that you can only use the definition. You cannot just say, well, it's trivial, because you have only to use the definition. So let's do the other integral of a phi plus b psi, integral a phi plus b psi.
We proved it for scalar multiplication, and for addition it is obvious.
That's key. Do you agree?
We did it for scalar multiplication.
Okay, so A we remove. So only for
We also make the intersection same trick to make the.
Again, we need to use the intersection. Because now, with this notation, phi plus psi is the sum Ci plus dj but Eij, so the intersection of j. And now, okay. So now we compute, so the integral here is the sum by definition well, you have also to use something like, you have to put d0 equal to 0 in the complement, but I don't want to enter. There is some glitch here. And now if you sum, now you split. And when you sum over j, well, you have to, you see.
Becomes EI.
Becomes this guy. So there exists a little bit of a trick.
But if we
If
fix I and sum over all j's, isn't this the same as EI?
No.
No, I have an EI and I distribute it between some FJ. So if I sum over all these such J, I recover the same thing.
Only two sets. Well, but it's already there. It's just that I can add the value 0. If I add the value 0 to the rest of the set, then this is 0, and so I recover all the rest, no? So I said plus, for example, here I add plus the measure of the, well, here it works because one is less than the other. Here is not working because I have to add the measure, so the rest of the measure. So essentially I say d equal to 0 in the rest. So here I put d equal to 0, d1, and here I put c equal to 0, and here c1. So I just can add an element whose measure is 0, whose coefficient is 0. So now it works. So concluding, the integral is additive with respect to the, well, here I never put the, you don't need, because if I put something here, essentially it's like intersecting all the sets with the domain of integration. So it's can't be additive with respect to the domain of integration. It's linear and it's monotone. So these are the properties. And I think we finish here. Yeah.